All right, welcome back to another video. And today we're going to do finding partial sums of telescoping series. So these are series, so we're going to be adding up a bunch of terms. And it's called telescoping because it's like a pirate's telescope. You know, he takes it out and he expands it and he looks out at the ocean. And then he puts it back down and he collapses it and stuffs it back in his pocket. So it's the same kind of idea with these. They're going to expand, they're going to get really long at first, but then they collapse down into something very small and more manageable. So you're going to see how that works. And the way that today's video is going to be structured is we're just going to have three examples. And the first two examples are going to be structured very similar to what you're going to see on the homework. And the third example, the directions are just going to be slightly different, but it's still very similar to what you're going to see on the homework. So with that said, let's just jump right in. So the first example is this one right here. So let's find a formula for S sub n for this guy. So the first thing we have to do is actually find a formula for A sub n for each individual term. And you're probably noticing that there already is a nice nice pattern for that. Let me go ahead and set this up here. If we look at just the numbers in the numerator, well, that's super easy. All those numbers are just 3, so we know the numerator is going to be 3. In the denominator, if we look at just one factor at a time, so we've seen this before, if we look at just the first factors, for instance, 1, 4, 7, 10, they follow a nice pattern. It's arithmetic. They increase by 3 each time, so we know that that's going to be 3n minus 2. And then finally, the last factor, the second factor in each fraction, that's also arithmetic, 4, 7, 10, 13. They also increase by 3, so we know that that factor can be written as 3n plus 1. And now we have a nice, rather simple expression for A sub n. Now that we have that, we can use that to easily rewrite the series as in sigma notation. And so that's simply just going to be the summation of 3 over 3n minus 2, 3n plus 1, as n goes from 1 to infinity. Okay, so now we have that. Now here's where the fun starts. So now to find the formula for S sub n. And the way we're going to do that is if you take a look, first of all, at this right here. In fact, specifically at the argument. This is a rational expression, meaning the top and the bottom are polynomials. In fact, the bottom is factored. That's even more important. That means that we can go ahead and use partial fraction decomposition to write this. So yay, we get to remember how partial fraction decomposition works. Don't worry though, if you remember partial fraction decomposition from before, it actually fell into two camps. There was one camp that was fairly straightforward, not too bad, and then the other one that was just like really tedious and became really complicated. These are all going to be the more straightforward ones, which is nice. So we're going to use partial fraction decomposition to rewrite A sub n. So in case you forgot how that works, we make an equation first of all. So we're going to have the original, and we want to break it up into two fractions, and each factor gets its own fraction. We just don't know what the numerators are, so we're going to solve for a and b. And then what we do behind the scenes, we normally don't write this. For this first example, I'm going to write it, but then I'm not going to write it again. But we have this equation, and we want to find the values of a and b that will work. So we multiply this by the LCD. And the LCD in this case is 3n minus 2, 3n plus 1. And remember, if you've done everything right, if you've set this all up right, your LCD should always be the original denominator. If it doesn't equal the original denominator, go back and check your work. You're doing something wrong. Okay, so now we got that. This denominator will, or the LCD will cancel out with the entire denominator of the first fraction. So we're just left with the numerator. When this distributes to the second fraction, the one with the a, the 3n minus 2's will cancel, but we have a times 3n plus 1. And then, similarly, with the last fraction, the 3n plus 1's cancel, so we'll have b times 3n minus 2. All right, so then now we have to find out what's going to work here. And the easiest thing, you can plug in anything for n. The easiest thing to do, since these are linear factors though, is just figure out what value of n makes each factor equal 0 and plug that in one at a time. So for instance, if we let n equal negative 1/3, and I did that because negative 1/3 will make 3n plus 1 equal 0. So if I take negative 1/3 and plug it in for the n's in all of this, well, the left-hand side's still 3. Negative 1/3 is going to make this equal 0, and 0 times a is just 0. So this completely goes away. And then over here, 3 times negative 1/3 is negative 1. And negative 1 minus 2 is negative 3. So we have negative 3b. And so b is negative 1. So with very little work, we already know what b is. We're going to do something very similar, and we'll be able to figure out what a is. So the other factor that we had in this is 3n minus 2. So what's going to make that equal 0 is going to be 2/3. And we plug that into this equation, and we get 3. 3 times 2/3 is going to be 2, and 2 plus 1 is 3, so we're going to have 3a. And over here, the you're going to, when you let n equal 2/3, you're going to get 2 minus 2, which is 0, so this whole thing goes away. And now we know what a is. So now we know that a sub n can be rewritten. Instead of using this fraction, we can rewrite it into these two fractions. And so it'll be a over 3n minus 2 minus b, or plus b actually, plus a negative 1 over 3n plus 1. Okay, so now that we have that, what we're going to do is we're going to rewrite the sigma, but using this. And I'm going to do it a little differently too. So this was, the way the original series was written, it was written as an infinite series. And so that's why to say equals, I actually had to write it as an infinite series in sigma notation. I had to go to infinity. But remember, and I didn't put the directions here, but our goal is to find a formula for the nth partial sum. So we're actually going to stop somewhere. We're going to stop at some value n. And so when I start setting this up, I want the nth partial sum as something that stops at n. If n is my upper limit, I need a different variable that's the index of summation. And you can use whatever you want. I, j, k are very typical to use, but there's nothing that says you have to use one of those. But I'm going to use an I, and whoops, I need to have an I in here too. 3i minus 2 minus 1 over 3i plus 1. So don't be too confused by the fact that I changed the variable. It's just a variable. Like I said, it could have been anything, but I'm going to use n for my upper limit now. So whatever I use here just has to be something other than n. So what I have, kind of looking back at all of this now, this series, each term can be written like this, but I've just decomposed it into this fraction. So now each one of these terms can also be written like this. So now I'm just taking the sum of those terms, but I'm going to take the first n terms. And let's see what we get. So now here's where the telescoping part's going to come in. I'm going to expand it by hand, first of all. So I'm going to let I equal 1 and plug it in. I'm going to let I equal 2 and plug it in. I'm going to let I equal 3 and plug it in. I equal 4. And I keep doing that until I see a pattern. So when I is 1, We're going to have 3 times 1 minus 2, which is 1. So we're going to have 1 over 1. And with these, I never simplify them because often if you do, you miss the pattern. So I'm just going to leave it as 1 over 1. It's not our final answer, so we can do that. When I let I equal 1 in the second fraction, it's 3 times 1 plus 1, so that's going to be 1 over 4. So that was when I equaled 1. Now I do it again, but I'm going to let I equal 2. So 3 times 2 minus 2 is 4, and 3 times 2 plus 1 is 7. And I'm going to go again. And actually, I'm going to move this down here because I want more room. So then I let I equal 3. 3 times 3 is 9, minus 2 is 7, so it's 1/7. 3 times 3 is 9, plus 1 is 10, so it's 1/10. And so hopefully you see some patterns already happening. So one pattern, like now with the expanding, there's definitely a pattern. We have 1/4, 1/4, 1/7, 1/7, 1/10. We're probably going to have 1/10 here. And if you look at these denominators, 1, 4, 7, 10, they go up by 3 each time. So it seems like that's our pattern. And if we plug in just when I equals 4, just to double check, 3 times 4 is 12, minus 2 is 10, which we expected. 3 times 4 is 12, plus 1 is 13. I think we found that pattern. So that's one of the patterns. But how does that help us? Well, so now here's the telescoping part. We've just expanded it. We've just lengthened the telescope. But now, you may have also noticed, hey, wait, things are canceling. This negative 1/4 and positive 1/4 cancel out. And this negative 1/7 and positive 1/7 cancel out. And this negative 1/10 and positive 1/10 cancel out. And it's going to keep happening. The negative 1/13 is going to have a positive 1/13 to cancel out. So each fraction in each set of parentheses, the second fraction is going to cancel out with the next first fraction. And this will happen until you get to the very end. So let's see what happens at the very end. So the last thing I'm going to plug in is an n. So each one of these i's is going to become an n. And I'm going to have 1 over 3n minus 2 minus 1 over 3n plus 1. Now let's think about what cancels out. In each set of adjacent parentheses, the second fraction from the first parenthesis cancels out with the first fraction in the second one. So think about at the very end. What's going to end up canceling out here? Well, this first fraction is going to have something to cancel out with ahead of it. But this guy, he's not going to have anything to cancel out with after him. So he's going to be left. And actually, I also should have canceled out this negative 1/13 because it would have something to cancel out with it. So everything ends up canceling except the very first fraction and the very last fraction. So even though we may not know how many terms are in between and what they exactly look like, we know we're going to be left with this fraction and that fraction when everything else cancels, when it collapses like a telescope. And so we can condense this down to 1 over 1 minus 1 over 3n plus 1. And that's basically our formula for S sub n. We're just going to simplify it now and combine it to one fraction. But there's our formula. No more dot, dot, dot in there. And so let's go ahead and simplify it and combine it to one fraction. So that's really 1 minus 1 over 3n plus 1. Getting a common denominator, we can say 3n plus 1 over 3n plus 1 minus 1 over 3n plus 1. And finally, when we combine the numerators, the plus 1 minus 1 cancels out. So in the numerator, we're just left with 3n, and in the bottom, we're left with 3n plus 1. And we have a formula for S sub n, for the nth partial sum. And voila, there is our first example. So again, let's just do a quick recap of what we did, because they're all going to work the same way. So the first First thing to notice, by the way, is these are fractions. Nothing else that we've been doing has been fractions, so that's going to be a dead giveaway. You've got telescoping series when you got fractions. But anyway, our first thing was we needed to rewrite each term as we needed a formula for a sub n. And then we used partial fraction decomposition to rewrite that expression. And then we could go into writing it as a sigma, and then we could expand it, see the pattern of what collapses, take what's left, and combine it all into one fraction. So if you want to go ahead and do the homework, that's basically it. We're going to do another example just so you can get a feel. And the third example, though, if you skip the second example, it's just going to be a rehash of this. It's one you can try on your own. But the third example is going to be, it's the same idea, but it just gets more complicated. So I would encourage you to at least jump to the third example to see how that works. But let's take a look at example 2. I'm going to go to a new page. So example 2 is going to be this one. Okay, so we have to do what we did before. We still have to write a formula for a sub n. Definitely looks like the numerator is going to be a 1, but what the heck is going on in that denominator? So you could, if you wanted, you could look at just the denominators. 8, 15, 24, 35, and so on, and try to do the techniques we've done in the past, just looking at those numbers. It's not arithmetic, because they're not increasing by the same thing. It's not geometric, because we're not multiplying by a common ratio. If we tried finite differences, oh, well, look at that. It looks like the second differences are going to be the same. So you could do finite differences with this, and that would totally work. But if you remember the lesson from last week, I talked about how you can, but first take a look and see each one of these is a composite number, 8, 15. We can write it as a pair of factors. And if you just stop and slow down before jumping into finite differences, you'll be able to rewrite each of the fractions like this. And now it's like that first example. 2, 3, 4, 5, 4, 5, 6, 7. Oh, look at that. We have a nice pattern, nice arithmetic pattern in the factors. So I would encourage you at this point, go ahead and stop and try to figure out the formula for a sub n, and we will compare our answers. All right, so this is what you should have gotten for a sub n. 2, 3, 4, 5, it increases by 1. And so n plus 1 is going to be your formula for that factor. And 4, 5, 6, 7 also increases by 1. So 1n plus 3 is going to be your factor for that, or your formula for that factor. And then remember that means that this can be written as the summation of 1 over n plus 1 times n plus 3 as n goes from 1 to infinity. So looking at the infinite sum, that's what we have. But now let's go ahead and do partial fraction decomposition and see how that works. So I'm going to, again, pause the video, let you guys, or encourage you guys to pause the video and see what you get for partial fraction decomposition. We'll compare our answers and continue from there. All right, so this is what you should have gotten with that. Again, setting up the partial fraction decomposition, you have this line. Then when you multiply both sides by the LCD, which is this denominator here, the entire denominator will cancel out with here. You get 1. When you multiply by this denominator over here, the m plus 1s cancel, so you have a times m plus 3. And then over here, the m plus 3s cancel, so you have b times m plus 1. And then again, look at what makes each factor equal 0. What makes n plus 1 equal 0 is a negative 1. And you'll find that you get a is 1/2. What lets n plus 3 equal 0 is negative 3, and you find b is that. So when you plug those values in, these are fractions now. You can write the answer like this, but since they're both 1/2, I actually factored out the 1/2, and I'm going to have this instead. And you'll see that this ends up making it easier to work with in the next step. All right, so now that we have partial fractions, now we have it decomposed, now we rewrite it as a sigma, but remember our upper limit is going to be n, so use a different variable instead of n inside the summation. And then expand it, see what cancels, and see what you're left with. So again, I encourage you, pause the video and we'll compare our answers. Okay, I haven't fully worked it out yet, but I wanted to point something out with this one. So when I expand it, I do see things canceling out, but they're in different positions than before. So I've only canceled it, but I haven't written the stuff at the end. But I do see that there's a negative 1/4 and positive 1/4, and then a negative 1/5, positive 1/5, and a negative 1/6, positive 1/6. Like there's a definite pattern to what's going to cancel. And that's what you're looking for, is stuff that follows the pattern. So those will cancel. Notice here's a quantity. On either side of the quantity is what cancels. So then the same thing happens with the 1/5. Here's another quantity, and the 1/5 are on either side of it. Here's another quantity, and this time it's going to be the 1/6 that are going to cancel. And then so on and so on. This negative 1/8, there's a quantity. It's going to have a negative 1/8 on one side and a positive 1/8 on the other side that's going to cancel. But this time we have two fractions in the front that weren't able to cancel. So that means we're going to have to rethink what we put here at the end. So here's the way I think about it. This right here at the beginning was when k equaled 1. This right here was k equals 2. So these two fractions I got from plugging in when k was 1. These two fractions I got from plugging in when k was 2. I have something left in each one of these. I have a 1/2 and a 1/3. It took two expansions to have what I was going to have left. So that means at the end, I also need two expansions. I'm going to have this expansion and then this expansion. This one, the very end, is when k is n, because that's my upper limit. That's where I end. But right before it is when k is n minus 1. And so I need both of those. So I'm going to go ahead and let k equal n minus 1 in the first fraction. So n minus 1 plus 1 is just going to be n. And then if I let this k equal n minus 1, then an n minus 1 plus 3 is n plus 2. And so there's that one. And then for the last one, I let k equal n, and I have 1 over n plus 1 minus 1 over n plus 3. And now it's going to be very symmetrical to figure out what's left. It's the first fraction in both of these. So symmetrically, like the mirror image is going to be the last fraction in both of these. So this one and this one will both be left. And don't forget that there's minus signs in front of them. But this n plus 1 over n plus 1 would have something here to cancel out with. So it's going to be gone. And then this 1 over n, there'd be a quantity here and it would have something to cancel out with. So it's also going to be gone. So again, it's very symmetrical. Counting, if you count from the beginning and count the fractions, first, second, third, fourth, fifth, sixth, and so on, it's the first and the third fraction we're left with. If you count from the end, then counting from the end, it's the first and the third fraction you're left with. So it gets a little more complicated sometimes, but eventually you'll see the pattern of what cancels. And so S sub n is 1/2. Don't forget about the 1/2 out in front. And then it's 1/2 plus 1/3 minus 1 over n plus 2 minus 1 over n plus 3. And now you just use your algebraic skills to find an LCD and combine that all into one fraction. So pause the video again if you want, and I'm just going to work that out. Okay, so it gets a little long at first, but it collapses pretty nicely. You should have found your LCD to be this. Oops. Oh no, I thought I forgot a parenthesis. So you have that. And then I went ahead and put it all under one fraction already. The first fraction had a 2, but you still needed a 3 times n plus 2, n plus 3. So that went in the top. The second fraction already had a 3, but you needed a 2 times n plus 2, n plus 3. The next fraction had an n plus 2, so you needed 6, n plus 3. Whoops, right there. And the last fraction had an n plus 3, so you needed 6, n plus 2. And then I distributed everything and combined like terms. I just factored out the n and put it all together in a nice factored form. Nothing cancels, so there's your formula. And there is a formula for S sub n there. So that's example 2. Now we're going to do one more example, like I said. This one gets a little more complicated in seeing what cancels, and you will have a couple of problems on your homework like this, but the idea is exactly the same. So let's take a look at that one. All right, so here's example 3. And you can see the big difference is now it's got 3 fractions in it. So I'm already jumping to the last part of it where we got a formula for a sub n. We've written it as a sigma. But now we're going to have to go ahead and do the same steps. So if you want to pause the video and try this on your own, I definitely encourage you to. Like I said, it just takes a little more steps to figure out what's going to cancel and what the pattern is. You may need to expand it a little bit further than what we've been doing in the first 2 examples to really see that pattern. But there's really nothing else that's different about this except it's just a longer problem. So if you want to try it, go ahead, and we're going to do the first part. So the first part is really just partial fraction decomposition. So I'm going to work that out and put that on the screen. If you want to also try working that out, try doing partial fraction decomposition on this part right here. Okay, so I've partially worked out partial fraction decomposition. Did it mostly. So again, set up your partial fractions, multiply by the LCD, you should wind up with this equation. And then one at a time, what makes this factor equal 0 is k equals positive 1/2. And you plug it into each one of these. When you let k equal 1/2 here, you're just going to get 1. When you let k equal 1/2 here, let's see, we have the a. 2 times 1/2 is 1, 1 plus 1 is 2. And 2 times 1/2 is 1, plus 3 is 4. But when you plug it into here, each one of these factors becomes 0, so there's nothing left. So you just have this, a is 1/8. And similarly for b and c. Now for the next part, and this again only because I know where we're going with this, just like I did on that previous example when we had the fractions, I want to be able to factor out the fraction. And in order to factor out the fraction, it's going to be easiest if they have a common denominator. So I'm going to go ahead and change this to 2/8. That way, when I rewrite the summation, and I can say S sub n equals the summation, actually, I'm going to put this here. I'm going to factor out the 1/8, and that way we can just put a 1 for A and a 2 for B and a -3 for C. So it will look like 1 over 2k minus 1 plus 2 over 2k plus 1 minus 3 over 2k plus 3. And then it's as k goes from 1 to n. So there's the partial fraction decomposition and the setup of it. And you don't have to factor out the 1/8. It's just easier, I think, when you do the expansion part. So again, now that you got that, if you want to pause the video and try the expanding part, go ahead. I'm going to go ahead and expand it, and we'll take a look and see what it looks like. All right, so this is what we get when we expand it. And hopefully with 4, it'll be enough to see. And you may go, well, gosh, I don't see anything. I don't see any pairs or fractions factor or canceling out. And you're not. But remember, the original problem had 3 fractions in it. So we're actually going to look for triples that cancel out. And If you want to pause the video now to look for triples, maybe that's where you were getting caught up, go ahead and do it, but I'm going to show right now. All right, if we take a look, we have this fraction and this fraction and this fraction all with a denominator of 5, and they will cancel out. 2/5 and 1/5 is 3/5. That cancels out with a negative 3/5. So they're gone. And then the next set, well, the next triple that I see are 7s. And again, they're kind of in that same position. If you notice, it took 3 expansions. The middle fraction cancels out with the last in the previous and the first fraction in the next one. Same thing here. The middle fraction is going to cancel out with the last in the previous expansion and the first in the next expansion. And 2 7s and 1 7 cancels out with negative 3 7. So now these guys are gone. And we can do one more. We can see the 9ths are canceled. And see, this is what I was talking about before. I don't simplify. If I had simplified this 3/9 to 1/3, it may have been harder to see. And especially if that had come up in the beginning, like that might have thrown me off. So I never simplify because you're going to want to be able to see what cancels really easily. But 2/9 and 1/9 is 3/9. That cancels out with a negative 3/9. So these guys are gone. So now let's see what we're left with. So like I said, it takes 3 expansions to cancel out. So this 2/11 is going to cancel out with the negative 3/11 there, and we would have a fraction after it. So these guys are gone. And then the same thing here, this negative 3/13 would cancel out with the next 2, so that one's gone. But right here, we don't have anything. This 1/3 has a 2/3 in front of it, but it would need another fraction in front of it to follow the same pattern, and it just doesn't exist. So these guys are not going to cancel out. And then likewise, same here with the 1/1. It would need something in front of it, and then another thing in front of it. I'm not even off the screen. So that guy is also still here. So that means, sorry. That means now if we look, it takes 1, 2 expansions to have what we're left with in the beginning. So we need 2 expansions at the end. We need to let k equal n minus 1. And then we need to look at when k equals n. So we need those 2 expansions. Last one would be the upper limit when k is n. And then we have to look at right before it. So if we let k equal n minus 1, just be careful, because remember this 2 then would have to distribute across there. So you'd have 2 times this. So you'd have 2n minus 2 minus 1. You'd have 2n minus 3 for that first denominator. Then you'd have 2n minus 2 plus 1. So that's 2n minus 1. And then finally, you'd have 2n minus 1. 2n minus 2 plus 3, you'd have 2n plus 1. And then for the last one, that's nice and easy. You just let all the k's equal n. So you have 1 over 2n minus 1 plus 2 over 2n plus 1 minus 3 over 2n plus 3. And then this is where I count the fractions to see what I'm left with. So in the beginning, starting from the first fraction, it's 1, 2, 4. It's the first, second, and fourth fraction. So starting from the end, it's the first, second, and fourth fraction that we're left with. So it's got that nice symmetry to it. So S sub n is 1/8 times 1 plus 2/3 plus 1/3 minus 3 over 2n plus 1 plus 2 over 2n plus 1 minus 3 over 2n plus 3. Making sure I have my minus signs correct, and I do. So that's what we're left with, and then we just combine it to a single fraction like before. Before I do that, though, I'm going to go ahead and combine like terms. So 1 plus 2 plus 2/3 plus 1/3, that's 2. Mm-hmm. And then I've got some common denominators here already. So combining the numerators, -3 plus 2, that's going to give me minus 1 over 2n plus 1, but then I still have that other fraction. All right, so my final step now, get a common denominator and combine all of that stuff together. So if you guys want to pause the video one last time and try it on your own, let's give it a go. All right, so here's the final work. There was my LCD. So then I went ahead and put everything over the common denominator, combine like terms, and you end up with this. So there you go. There's telescoping series in a nutshell, and have fun with your homework.